I thank you for this wonderful opportunity, and I'm glad to show you the chromatographs and detectors in this chemistry lab. Let's start with a gas chromatograph here. You probably know that chromatography is not as used as a liquid chromatography. And anyhow, the gas chromatography still enjoys some niche applications in the pharmaceutical sector, for example, as regards volatile organic compounds from any preparation. But now we will focus on the liquid chromatography because obviously many pharmaceuticals are not volatile or volatilizable, so they are not able to be analyzed by gas chromatography. Here we have an ion chromatography, and here we have the liquid HUPLC chromatograph. So usually pharmaceuticals have an acid-base chemistry. So if they are ionized or ionizable, they can be analyzed by the ion chromatograph. Just a moment. Okay, here we go. Here you see the hydraulic circuit of the chromatograph, and the effluent from the bottle enter the degasser here. The degasser is crucial because dissolved gases would form a bubble in the detector, which is at the lowest pressure in the whole chromatographic hydraulic circuit. So bubbles are very detrimental, and we need to eliminate dissolved gases to prevent bubble formation. The degasser here is actually a membrane pump which will suck out dissolved gases from the solution. After the degasser here, you can follow here the circuit, the tubing, which enter the pump system. We have two piston pumps. They are reciprocating volumetric pumps. We have two pumps because we would like to deliver a flow as smooth as possible, but we will see that we also need a dampener later. Anyhow, the liquid enters in the first head of the pump, and here you see there's a valve, because if the pump is in cavitation, we have to suck the liquid from here to amend the problem from here. From the first pump head, we go here and here to the second pump head. This pump head has two outlets. The first one goes to the waste here, while the second one, with the narrow tubing, goes to the column sooner or later. And we have check valves inside the pumps to provide us with a one direction flow. And why we find here also a valve. This is called the purge valve, and it enables us, it enables the priming procedure. Okay, what is priming? Priming is the purge procedure. Well, when we need to switch from one effluent to another, we have to wash the entire hydraulic circuit very quickly. So we have to go, for example, to 3 or 5 milliliters per minute. In this case, such a high flow rate would not be compatible with the column. Hence, we have to open the purge valve and divert the flow towards the waste, just to wash the system very, very quickly. Okay, if the purge valve is closed, we go on with the hydraulic circuit and we meet a sensor of pressure. This is the sensor of pressure. Why do we need to monitor the pressure? According to the Poiseuille law that you see here, okay, if the length of the tubing increases, the pressure is higher. If the viscosity of the eluent increases, the pressure is higher. And the pressure increases also with the decreasing of the radius of the tubing, and it increasing at lower temperature. So actually the system is a high pressure system because the column is packed, is finally packed. And so for this reason, we have to monitor the pressure. What happens, the pressure, the sensor of pressure here, is very important because if the pressure increases very rapidly, probably the system is clogged. What might have been happened? If we are not careful, the mixing of a buffer with ions, for example, with methanol, could provoke the precipitation of the buffer due to the lowering of the dielectric constant of the eluent. In this case, the sensor of pressure would alert us and the whole system would stop. And this is very dangerous, I mean, because we have to replace some parts, for example, the check valves of the piston. But you know, in chromatography, pressure may also increase gradually, step by step, little by little, day after day, because particulate matter can build up inside the column, and this just means that the column is quite old. What happens if the pressure is too low? Again, the pump would stop. Probably you have left the purge valve open after the priming procedure. You forget to close it and the pressure is very low. In this case, the system alerts us again and would stop the pump because the flow is not the set point flow. But what happens if the system, if there's a very small leakage? A very small leakage, let's say, for example, 1 drop per minute or something like that, would not be detected as a massive decrease in the pressure. For this reason, the drops would get inside a vessel here, a small vessel. Here you find a conductivity meter. If the vessel is full with the eluent drops, the conductivity would touch the liquid and would alert us that there's a small leakage. The constant flow is very important to have a reproducible, to have reproducibility. So the system would alert us again. Well, I told you that we have two pistons to provide us with an almost constant flow, but the flow is actually not completely constant. And the pump delivers a series of strokes of pulsation. For this reason, after the sensor of pressure, the liquid, the eluent, will get inside here, okay, will get inside here the dampener. You cannot see the dampener because the dampener is behind this front panel. But the damper is like a coil, a spring. When it feels the stroke, the pulsation, the spring would expand, thereby absorbing and storing the excess kinetic energy of the pulsations. And when the pulsation, when the stroke, when we have no strokes, the expanded coil would return to the original position, thereby delivering an extra flow of liquid. And so in this way, we can almost eliminate pulsation and pump strokes. After the dampener here, we go from the dampener, from the outlet here of the dampener, we go to the Raildyne. The Raildyne system is an injector that enables the injection itself. You know, in chromatography, we use a syringe to inject the sample. In liquid chromatography, we use a syringe not to inject, but only to load the injector. When I load the sample via this syringe, here, the sample goes inside this Raildyne loop. Okay, the loop has a fixed volume. In this case, is 25 microliters, but it can be also 5 microliters of what we need actually. It goes inside the loop, and the loop has an established volume. So if I load an extra volume of sample solution, it will go to the waste. This way, I'm sure that I have loaded a precise volume of sample at ambient pressure, and I'm able to push the piston of my syringe at ambient pressure. What happens now? If I rotate, you know, we have a rotor and a stator. If I rotate via the software, obviously, the Raildyne injector, it happens that the loop, the sample contained in the loop will go to the column, because now the pump is connected to the loop, and so the eluent will push the sample plug inside the column. In this way, the high pressure ambient is separated from the low pressure one, and after loading, I can actually inject my sample plug inside the column. Here we have the column. And, okay, the column, if we are analyzing cationic or anionic drugs, have different configuration. In the cationic configuration, the stationary phase of the column here is a resin-bearing sulfonate groups, which are negatively charged. And so they're able to interact with the basic drugs, basic analytes, which are usually protonated. And in this case, the allotropic strength is given by the pH of the eluent. If I lower the pH, its allotropic strength will increase, because H+, the H+ ion, is a good competitor for any cation. And so the cation, finding this competitor, are pushed towards the detector, are eluted. Okay. Instead, in the anionic configuration that we use, for example, with acidic drugs, for example, or ions, also inorganic ions. Think about fluoride in a toothpaste or something like that, for example. Well, in the anionic configuration, the stationary phase is a resin, okay, with quaternary ammonium groups positively charged, which interacts with acidic and negatively charged analytes. In this case, the column effluent from here could not directly go to the conductivity cell, which is the detector, but need to be suppressed. What is suppression? What is a suppressor? A suppressor is a device which increases the signal of anionic analytes and decreases the signal from the background noise. How does it work? A suppressor usually electrolyzes water to produce H plus and OH minus. In this way, you know, if we are in the anionic configuration, we have a lot of OH minus hydroxyl ions in the effluent, which are highly conductive. If I combine H plus from the electrolysis of water with OH minus, I get water. So the background conductivity due to the hydroxyl ions is drastically decreased. In the meanwhile, the H plus, the analyte ion negatively charged, for example, fluoride, will exchange its counter ion from sodium or potassium to H plus. This means that fluoride conductivity with H plus is increased while the background element conductivity is sharply decreased. This way, the signal to noise ratio is really increased and the limit of detection can be decreased. So we can see also trace concentrations. Okay. This is the hydraulic circuit of an ion chromatograph that, as I told you before, is useful for analytes, for drugs which have an acid-base chemistry. Now I would like to show you the UHPLC with the column compartment, the pump compartment, the column compartment, and below with the detector, diode array detector compartment. Let's start with the pump compartment here. Actually, I will go through this compartment very quickly because the many parts are similar to the ion chromatograph hydraulic circuit, but there are some differences that should be emphasized. For example, you will see here that we have not only one bottle, but we have up to 4 bottles here, 4 elements, 4 channels, and instead here we have only 1 bottle, because in this system I can only have an isocratic elution. Instead, in HPLC, which is more versatile than the ICS system, I can create a gradient by the mixture of different solvents that provide the eluent. The 4 solvents and first enters, okay, the 4 solvents first enters the system, the chromatograph, here through the degasser. Each solvent will be degassed for the same reason, because otherwise at the end of the system here in the DAD, the diode array detector, where the pressure is lower, a bubble may build up and it would be again very detrimental. So after the degasser, they all go to the proportionating valve. You know, this valve has 4 inlets, but only 1 outlet. Why? Because the proportionating valve adjusts the flow of each solvent to a predetermined value, so that the final composition will be the one that we need. After the proportionating valve, the liquid would flow through the pump system. And again, we see here a purge valve that goes directly to the waste here. And if it is open, we can wash the system very, very quickly because we can go also at 3 or 5 milliliters per minute. If it is closed, instead, the effluent comes out from this outlet here and gets into a mixing chamber here. The mixing chamber here is full with little spheres. It is a 350 microliter chamber where, according to according to the flow among the spheres, the 4 solvents get completely mixed. From here, we go to the Raildyne. Again, you see here, because it is manual, that you can rotate the Raildyne from the load to the inject position. If it is in the load position, I can load the sample into the loop. When I turn the rotor, I actually inject what is inside the loop into the column, because the stream from the pump will pass through the loop and then it will go to the column itself. The column usually it has a stationary phase that is a reversed stationary phase, usually a C18 or a C8 stationary phase with a silica-based particles is commonly used, and the silica is derivativized with the long alkyl chains, and the reverse phase mechanism is operating there. So you will probably understand that this is very important in the pharmaceutical sector, where we have a very wide range of polarity for our analyze. And from the column, we go into a diode array detector that is here. The diode array detector here is a diode array because we need a very quick, a very fast wavelength scan. We cannot use a sequential wavelength scan, but we have to get all the wavelengths acquired, detected simultaneously to prevent the fact that in the cell here, analytes that were previously separated in the column could get mixed again. So I need a very, very fast detection. Well, the geometry of the cell inside the diode array detector is a Z geometry because we need to keep the optical path quite long, because if the optical path would be reduced, the absorbance, according to the Lambert-Beer law, would not be enough. For this reason, to keep the volume very small, but the optical part quite long, we use a Z geometry. Okay, now we go to the second moment of this presentation, and I would like to focus on the comparison among the different techniques. Well, as regard the injection, I already told you this is also a kind of summary of what in part I have just said. As regard the injection, we have a syringe injection in GC, but we need a loop and a Raildyne in liquid chromatography for the pressure issue. As regard the column time, we have usually a wall-coated open tubular column in the GC, while we have packed column columns in the liquid chromatography. And for this reason, we need pumps to make a flow in liquid chromatography, while we do not need pumps in gas chromatography. Also, the column length is different, since the columns are packed and the flow of a liquid is more difficult than the flow of the gas because of the viscosity of the liquid that is much higher than that of the gas. We can only have column length up to 25 centimeters, while the column length of the GC can also be up to 300 meters. So very, very different. The mobile phase, again, we have a gas in gas chromatography, while we have a liquid. We can have a gradient in the HPLC. We have to go isochromatically in IC, unless we are using IC for protein detection. And also now it is important to emphasize the mechanism of elution. In a GC, the accelerator pedal is actually the temperature, because the sorption of analytes would increase with an increasing temperature, since the sorption is an endothermic process. And for this reason, we usually increase the temperature to accelerate the process. Instead, in a reverse phase HPLC, we use the polarity. The higher the percentage of methanol or acetonitrile, and the fastest the analysis. And obviously, in ICS, in ion chromatography, we instead use the pH. We instead use the pH of the eluent. As I told you before, in the cationic configuration, if I increase the concentration of the H+, that is the competitor of our cations, we have an accelerated elution. Instead, in the anionic configuration, if I increase the pH and I increase the presence of the hydroxyl ions, I can increase the elution, the velocity of elution. What about the interface with the mass spectrometer? You saw the chromatograph, the gas chromatograph there, and it is a GCMS. The interface is very easy. There's a skimmer, there's a nozzle, and according to the Gram law, it is very easy to interface the two instruments. You will instead see that in HPLC, due to the interface is very complex, because the amount of molecules in 1 milliliter per minute of gas and liquid is completely different. So we have to get rid of a lot of neutral molecules, and the Gram law would not work in this case. So I will show in a very short while how we can accomplish this. So let's go to the detector, the excellent Q-exactive focus detector here. That is the another detector for liquid chromatography. I have shown you before that this is the DAD. There's an entrance and there's an outlet here. From the outlet, you can follow my hand. You will see that the outlet of the detector can get into a divert valve, where it can be diverted or to the waste there, or to another detector that is an excellent and very expedient detector, because it is a mass spectrometer, and in particular, it is an orbitrap. The first thing that we have to do is to ionize our analytes. Okay, and how do we ionize our analytes? You will probably see that the effluent of the column will enter from here this probe. This probe here has a needle and has a capillary, so the effluent from the chromatography will get into a capillary containing a needle. The needle is kept or receives a very high voltage, up to some kilovolts. That is very, very high. This way, analytes which have an acid-base chemistry would get or protonated if they are a base, or deprotonated if they have an acidic behavior. In both cases, for basic analytes, we use a positive potential to protonate these analytes. For acidic drugs, we use a negative potential to get them deprotonated. In both cases, the probe ends with a nozzle that now it is not easy to see what is inside, and for this reason I go back to my slide to be more for the sake of clarity. Well, the probe, the probe nozzle here, you can see the probe nozzle here, the effluent from the columns comes out here, and I told you that the voltage is very, very high here, and on the other side, I see a sweep cone that is also a kind of baffle or a skimmer, something that acts as a physical barrier because we do not want any molecule to get inside the detector. We only want ions to get inside the detector. Okay. How does the ionization work? In this case, we have an electrospray ionization. What happens? The eluent, as I told you, enters from here inside the capillary of the probe, and the probe has also two inlets for two different gases. There is a sheath gas and an auxiliary gas. Both of them are nitrogen. And which is their role? As I told you before, if I switch on the potential in the metal needle inside the capillary, a Taylor cone will develop because analytes are now charged according to the potential of the needle, and so an electrostatic repulsion will start. And what happens? The sheath gas is the inner coaxial gas that sprays and nebulizes the effluent into a fine mist of electrically charged droplets as it exits the metal needle. And the auxiliary gas aids solvent evaporation, and there's a shrinkage of droplets by solvent evaporation at constant charge. And so the density of the charge increases, and when the radius decreases below a certain critical value, fission into smaller droplets occurs, and there's a Coulombic explosion, and ions are ejected into the gas phase. You see here that the potential is applied, so ions are now attracted towards the interior of the mass spectrometer because of two reasons. The first one is the gradient in the pressure, because inside we have only 1 millibar, and the second one is the voltage gradient. and the geometry at 60 degrees prevents neutrals from entering the skimmer. And, okay, should go on, just a moment. Let's try this way, yes. And we have different screws to adjust the position of our probe and skimmer cone to maximize the ruggedness of the analysis and also the sensitivity of the analytical step. Now, what's beyond that front panel? What's beyond this panel? You cannot see what's behind this panel, but I can show you. After the sweep cone, we find S lenses that capture and focus ion for effective transmission into the mass spectrometer. And then we have a bent flat pole which filters out neutrals, neutral species, because the neutrals, if they have entered the system, neutral species would follow a linear path. They would not bend. Instead, and so this bent flat pole filters out neutrals. And then we have a mass filter that is a quadrupole that only eventually selects ion of interest. We will see it later. Then we have a C-trap which collects ion into small packets and stabilizes them. And then these packets are injected into the mass analyzer, into the orbitrap, where the frequencies of orbital motion of ions are related to their M to Z ratio. The Fourier transformation enables us to go from the time domain to the frequency domain and then to the M ratio Z values. Eventually, we may have a collision cell where collision-induced fragmentation may occur if we decide to fragment specific ions from the from that were previously detected in the full scan mode. Now that you know how the orbitrap detector works, we may have a look to our study. We have studied the liquid-liquid extraction for illicit adulterants in sport dietary supplements, and we tested 38 samples from the internet or from fitness leisure centers, and we checked the presence of 40 forbidden analyses. Which analyses? You know, there is a World Anti-Doping Agency who provide us with a list of, a very long list of prohibited drugs in competition or always prohibited drugs for athletes. And in this case, we selected 40 drugs. They are antidepressants, or stimulant, or anti-inflammatory, or diuretics. We also have, obviously, in leisure center, in fitness center, anabolic steroids and beta-2 agonists, and also sexual stimulants and so on. Well, as regards the design of experiment, we decided to use the design of experiment, first of all, in the pre-analytical step, that is the extraction. We usually, researchers all around the world rely on a methanol extraction procedure, and we decided to test this hypothesis. Is methanol actually the best extractant or not? To do so, we have prepared, we prepared 10 different mixture extractants, and the composition of each extractant will go from 100% of water or 100% methanol and 100% acetonitrile to the 33% of the ternary mixture. We have tested the extraction procedure with all these extractants, and we have used a quadratic model to test the influence of the composition on the recovery of a spike, on the recovery of our target analytes in a spiked sample. So the extraction, we can go very quickly through the extraction procedure. Anyhow, the 30 gram of the blank sample were weighted in a capsule, and the standard solution was added, and then it was homogenized. And this spiked sample is now extracted with 5 milliliters of each extractant, and then after vortexing and centrifugation, we get the injectable sample. So, I mean, we went from the sample to the injectable sample here. Okay, now I would like to show some basic of the software we have used, because let's go to the software of the mass spectrometer here. And first of all, we have to set up our instrument, and okay, you see that we have you see that we have two parts here. We have a Dionix chromatography and the mass section. The chromatography can be arranged via the wizard, so we can use the temperature control here with an upper and lower limit, and also ready temperature delta. And we can obviously choose to perform a multi-step gradient. We can give the name of the solvent here. For example, this is water and formate buffer. And here we have methanol and formate buffer. Okay, and we go next. Now, I think we don't have such a long time to edit all the gradient, but you can see the gradient from here, the edited gradient from here, and the curve will enable us to perform also convex or concave gradient. We allow 5 minutes equilibration when the run is over, and after this step, we can go to the UV, the DAD detection, okay? We can set the chromatography runtime, and we can set the wavelength in this panel. And once you have finished, the program is here. Then we have to go to the mass spectrometer setting. First of all, we have to choose the kind of analytes we want to analyze. This is accomplished from an inclusion list. The inclusion list should be prepared in advance, and I can import the inclusion list from here, for example. Let's have this inclusion list, okay? And now I have all the exact masses, the name of our analytes, and the polarity that is always positive, obviously, because we have basic drugs. And with this inclusion list, what happens? When the full scan experiment detects one ion in this list, this ion is subsequently selected by the quadrupole, and it will trigger the presence of the specific ion in this list, will trigger its fragmentation in the collision cell. So we have a collision-induced dissociation. Well, well, I have shown the inclusion list. Now I have to tell you that obviously to obtain a reasonable and an efficient ionization, we have to select proper parameters for the ion max ionization source. Usually we go and look for a specific file that should have been prepared before. Let's go with the default file now. Now we have, once we have organized our user-defined inclusion list and the parameters for the ionization, we have to choose the experiment. We now select the full scan, that is the more informative experiment, and by selecting here, not a standard, but an advanced role, user role, we can choose to go on a tandem mass spectrometry, and we choose the confirmation procedure, just to do what I told you before. If I find an analyte, an ion of a user-defined, of an analyte that is included in my inclusion list, I have to confirm its presence, and to do so, I trigger its dissociation in the dissociation cell. These parameters should be obviously edited. And what happened now? I go quite quickly, and I go to, here you have the condition. If you are interested, I can send you this condition, optimized condition, but I will go to our results. To go to our results here from the software, I have to go to another part of my software. I mean, to the, after the sequence setup. If I need more than one sample, I will prepare also a sequence, but I skip this step. I will go to the qual browser section to open a file that was previously done. Let's go down just a moment. Okay, I will check, for example, a standard. Okay, now you see here the raw chromatogram, but you are enabled to extract the from this raw chromatogram myriads of information. I mean, for example, if I ask to use just a moment, I have to enable the pin here, and then I go to the ranges here. Well, if I want to see a specific analyte in my sample, I will not display the total ion current, but I will detail a specific mass range. For example, the mass range of dopamine, that is 154.0863, for example. And in this case, what happens? All what is not dopamine is not shown anymore. I see the peak of dopamine, only of dopamine. I can work a lot with the software. It's not easy, but I will now go to our results. Here you see the chromatogram, the extracted ion chromatogram for our analytes, many of them, okay? And from this analysis, we have prepared calibration curves, and now we go to our results and to the conclusion, obviously. Our quadratic model, recovery fitting, obviously finds the best extractant solution for each analyte. I mean, each analyte has its own best extractant solution. Anyhow, and you can see this from, okay, and you can see this from these maps. And anyhow, just to conclude, we can say that if we want a multi-residue analysis, we have to use the best extractant solution is a ternary mixture that is 33% in each component. And when we use this extractant solution to analyze real samples, only 2 out of 38 samples were found positive, with a concentration higher than the limit of quantitation. And okay, for example, synephrine was found and ionization was found at this concentration. So as a conclusion, I would like to say that the sign of experiment was crucial to prove that even if researchers usually rely on methanol as the best extractant, this is not true, and it gives actually acceptable recoveries only in a few cases. So it is necessary to continue to be cautious in the purchase of food supplements, and now in the future we are going to further study this sector because it is very, very interesting. And please let me thank you for your attention and for the opportunity to speak to you. And I would like to thank my colleagues and my students, and Matteo Luisi in particular, and certainly the headmaster of my institute, Professor Margherita Bonanni. Can I hear you, perhaps?
Thank you, ma'am.
Okay? Yes.
Thank you, ma'am.
Yes.
Thank you, ma'am. Thank you for your wonderful and informative live session.
Thank you for...
Your explanation is very clear, ma'am. Definitely, this session will be helpful for our all students, research scholars, and all the research faculty members also. And we are grateful to you, madam, making time your busy schedule to accept our invitation and to speak about chromatographic methods and all. Thank you, madam.
Thank you all. Thank you all.
And I request Dr. Jagdish Panda sir to speak a few words. As we have
any questions?
We don't have any questions sir till now. Sir.
Any questions?
Sir, no questions from the participant side, sir.
You know, if there are any questions, I can also answer later in written form, no problem.
Okay.
Okay?
Sir, one question from Vivekanand Prajapati.
Yes, one way to reduce the noise, okay, now I see I can read. One way to reduce the noise during analysis, for example, if you are using an IC, ion chromatography, can be the use of a suppressor. The suppressor would reduce the conductivity, the high conductive environment of the eluent by combining H plus and OH minus, for example, and in this way the conductivity would really be decreased because it's water that now you have, and water is not conductive actually. So this is one way, and another way is to use, and another way, if you have a mass spectrometer detector, for example, another way is to extract an ion of interest, filtering out all the ions that are only background noise. I hope it is clear. Or perhaps you can also use a constant temperature in the detection cell, in the conductivity cell. The thermostating of the conductivity would be another major way to decrease the noise of the background noise, obviously. To reduce the pressure of the column. Oh, well, this is a good question. Well, you have to use chromatography grade solvents because otherwise particulate matter in the solvents may clog the system. And if you do not filter properly the solvents, day after day, little by little, you will see an increase in the pressure of the system. But this is not, this is detrimental to the column. Probably you might use a pre-column. This way you can only need to change the pre-column, not the whole column. And this is a good way to, how can I say, to prevent the increase of pressure that we all experience. I hope it is clear. So filter the eluents and use a pre-column to avoid the clogging of the system. Yes, there are other alternatives to the diode array detector. For example, you might have the mass spectrometer, or for sugars, you may use the index of the refractive index of the solution. For example, sugars do not have chromophores, and for this reason, they are not able to be detected. They can't be detected. They can be detected if you monitor the refractive index of the effluent, or they can be detected via a mass spectrometer. I mean, mass spectrometer is actually the universal detector, that's the most universal detector that we may have. Can we analyze non-volatile samples by GCMS? Yes, obviously, yes, but you have to derivatize the analytes. For example, if you have a fat sample, think about a fat sample, the fat olive oil, for example. You are not able to analyze olive oil directly here, but you may produce fatty acid methyl esters that are now volatiles, and these volatiles can then be detected, analyzed and detected. Or if you have acid drugs, they should be signalized with derivatizing reagents, so that they are now volatile and they can be detected. So GC is useful for volatile or volatilizable analytes. Priming time before start of a new analysis. Yes, because usually some big bubbles build up in the system. If this is the case, the degasser would not be enough to eliminate the very big bubbles. For this reason, with the purge valve open, you wash the system and the very big bubbles go to the waste, and then with the system washed this way, you can start the analysis. So you prime the system in two cases. When you change the eluents, and you have to be very attentive because you do not have to provoke precipitation of buffer ions. And when you start any new analysis, just to eliminate very, very big bubbles that are not able to be eliminated by the degasser. The degasser, remember, is only useful to eliminate dissolved gases. Difference between wet and dry priming. Actually, we only use wet priming. I'm not familiar with dry priming, and in this chromatography, you only use wet priming for sure. Okay, this is a very interesting question. Okay, actually, the carrier gas acts, well, what acts, the allotropic strength in GC is not given by the carrier gas. As you write here, the carrier gas is not active, is only a carrier. What stimulates elution? I mean, what is the accelerator pedal in the GC is temperature. Since analytes are adsorbed onto the stationary phase, to elute them, we have to stimulate their desorption. But desorption is an endothermic process. For this reason, we increase the temperature to enable desorption. Carrier gas only gives, how can I say, only moves the molecules to the detector, but it doesn't stimulate the desorption. The desorption is only due to the temperature increase. In fact, actually, the gradient in GC and in HPLC is similar. Here you increase the temperature and there you increase the polarity. Why only use Poisson law in pressure? What's the role of this law in pressure? As I told you before, the Poisson law is very important because it relates any physical parameters, any physical parameter of the system and of the eluent to the pressure. Think about the packing. A very fine packing would result in a very strong friction. If the friction is high, the pressure is high. Now today, I didn't have time to talk about the reduction of particle size. If we reduce the particle size, actually, we increase the pressure, but we have a better efficiency. But we increase the pressure because the friction is higher. In the Poisson law, we see the friction, we see the length of the tubing. If the tubing, if the column is longer, the pressure is longer. And we also see the influence of temperature. If we increase the temperature and we monitor the pressure, we will see that an increase in temperature would result in a decrease of viscosity, and this decrease in viscosity would result in a lower pressure. So remember, the pressure is also related to the flow rate. If we increase the flow rate, the pressure would obviously increase, according to the Poisson law. So to conclude, the Poisson law is very important because it can anticipate the effect of the manipulation of a specific parameter on the pressure. Why are there fewer peaks in a gas chromatogram with longer runtime than with shorter runtime? Well, actually, the number of peaks in a chromatogram depends on the number of analytes which are present in the injection, during the injection, in the injected solution. So there is no fixed rule. I mean, we have fewer peaks if we have fewer analytes. And if we have more analytes, we have to increase the chromatographic run to enable their separation. So this question can be answered in this way. The main concept is that the number of peaks is related to the number of analytes. But please, I would like to emphasize that some peaks might not be, the peaks of some analytes might not be present in the chromatogram if, for example, the temperature in the gas chromatography is not enough to desorb, to make them desorb. So, and some peaks might be missing because they can be overlapped In this way, in this case, we can run a peak purity routine combining with a comparison among the spectral information at the base, at the peak, and the other base of the chromatographic peak to see if the peak is pure or it is not pure. It's known as high performance, not high pressure, because the high pressure is related to the particle size. When I was a student, the particle size was as big as 5 microns. Now we have particle size that is below 2 microns. For this reason, as I told you before, the decrease in the particle size results in an increase of efficiency. So everybody wants to decrease the particle size, but by doing so, the pressure will increase because the friction is actually higher. So the answer is, now we call the HPLC high performance because we were able to decrease the particle size so much that the efficiency and the performance is really increased.
Okay, Joindra.
Oh, well. Well,
So
the last one, okay. But I can answer you also later if you want. Anyhow, which is the role of the Lambert-B in this analytical technique? Well, the Lambert-Beer's law is important because the absorbance is related not only to the concentration of the analyte, but also to the optical path of the cell. And as I told you before, the Z geometry results in a acceptable long optical path with a minimum cell volume. So the geometry of the detector is actually due to the Lambert-Beer's law. So it is crucial. But in the Lambert-Beer's law, there's also another parameter that is the, okay, as you want. I think that the time is over.
Yes, madam.
Okay.
Enough?
If any other questions, if you have any other questions, you can reach me and I can answer. Okay. So thank you for this opportunity, and let me greet all the Indian students and scholars, and thank you for your attention again.
Thank you, ma'am. Now I request Dr. Jagdish Panda sir to say both of things.
Madam, it is a great pleasure to associate with you again, and indeed it is a great pleasure to hear especially we have seen the ion chromatography, ion pair chromatography, which we don't have in our college. We have the UPHPLC with us, but we don't have the ion pair chromatography. So that we have seen, and many of the participants. Another thing is that your lab is very excellent, and we observed the very good big screens in your lab, and that is also okay. We have to think, and we want to establish such kind of the big screens in our labs also, and very good equipments in your lab, and very good explanation. Everyone is understood very well, and the questionnaire section. The questionnaire section was also very wonderful, and on behalf of my management, on behalf of myself, my colleagues, and all the participants, I once again thank you for you and your team and your head of the institution for all. So Margaret, Professor Margaret, your head of the institution, for everyone, we thank you a lot. And once again, it's a great opportunity for all of us. And next again, on 10th, again, we will meet, madam. Thank you for all your support.
Thank you again to all of you for this opportunity.
Again, meet on 10th, madam.
See you next next Friday, sorry.
Thank you, ma'am.
Okay. Okay. Goodbye. Goodbye.